So today I'll start with Lorentz Group. So far we have discussed the different kind of compact groups. For example, mostly the UN or SUN type, and then we have talked about the orthogonal groups a bit. And so today I'll introduce a group which is called the Lorentz Group. So you might be familiar in the special theory of relativity, the Lorentz transformation. So those transformations form a group and which we call the Lorentz group. And this is a space-time symmetry. So this and also here the it is non-compact compared to the unlike the earlier ones. So the basic idea of the Lorentz transformation, as all of us know, you start with this x mu and then you just coordinate four coordinates. So we talk about the 3+1 dimension here. So this x prime mu is written as a function of f mu x, right? And from there you can define also the metric is g mu nu, and which actually helps to define the length in this case, which is g mu nu x nu, and which is also remain invariant. You change the coordinate. So under this transformation, so 0 sigma x prime x prime sigma. And as this is non-compact, so as we have discussed earlier, that the length square would be related to the very much similar to the Minkowski length. So that's the difference in the signature here, temporal part and the spatial part, right? And this is very much unlike the Euclidean length, where all the signs are basically positive. So now G mu nu is transformed. Instead of G mu nu, you can write down G mu nu as like 0 sigma del f rho del x mu and del f sigma del x nu. Okay, and the transformation f of x is linear, and the transformation matrix has determinant plus minus 1, which implies the determinant of this matrix is 1. And so you can define this x prime mu is equal to lambda mu nu x nu plus a mu. But a mu, you can see this is a kind of a translation. Okay, and the whole thing you can write down as a g function of lambda a and acting on this x. Okay, so now if you take a product of these two such consecutive transformation, you get another g which is function of lambda prime a plus a prime. So this is the group multiplication rule defined here. So now we can define two types of transformation. One is the Poincare transformation, where we define Lorentz transformation as well as translation also. You can see this we will call the Lorentz transformation, and this is the translation. So if you switch off the translation, so Poincare transformation reduces to the Lorentz one. So you can think of Lorentz is basically a subpart of this Poincare transformation. And the Lorentz transformation, which is dictated by this lambda mu nu matrix. Okay, so that consists of rotations and the boost. So now what is this Lorentz group? So all in this group of this Lorentz transformation. So this we have learned about the Lorentz transformation. So all such Lorentz transformations form a group which actually restricted by this metric relation, and this is the Lorentz transform matrix. Okay, so there are two things you have to remember: metric and matrix. So this is the metric and this is the matrix. Okay, so these ones satisfied for all those such transformations form a group which we call the Lorentz group. And here the lambda 0 squared is 1 plus this thing, so this is always greater than equal to 1. Now based on this determinant, as we have said, this could be plus or minus 1. So though we can define different kind of orthogonal or anti-orthogonal rotations. Okay, and then also we can have a lambda 0 0 greater than equal to 1, determine lambda equal to 1. This is refers to no reversal. But if this is lambda 0 is less than equal to minus 1, then this is a time reversal. And when for this condition, this implies the space reversal, and for this it will space and time both are reversed. Okay, this way you can classify. So now we can have this Lorentz transformation, and if we can think of it's like a departure from the unity, then you can write it down like delta mu rho plus omega mu rho, and ignoring the higher order term in omega like omega square and so on. And similarly lambda nu sigma, you can write it down in this particular form, and from there you can show that this omega matrices tensors are rank 2 tensors are basically are antisymmetric, and that you can prove at this level. Okay, so the parameter matrix is omega is basically antisymmetric with respect to this, and there's a 6 independent variables are there. So there are, out of the 6 there are 3 boost and 3 rotations. Okay, so these are the basically generators, 3 boost generators and 3 rotation generators. So you can see rotation generators is very much like 0 minus I. So it's like fixed one coordinate in the spatial part, and basically you rotate another plane, like fix the x plane, rotate the yz plane, and continuously doing 3 independent rotations. Okay, immediately you have a 3 independent boost as well. So total you have a 6 generators. Now, how do we construct the Poincare algebra? They consider the product and this u lambda I, u1 plus omega epsilon, u inverse lambda I, which you can write it down as then different u. Okay, and here u1 plus omega epsilon equal to minus half omega mu nu j mu nu plus epsilon mu p mu, and so on. Okay. So once we expand that and we perform the matchings and all those things which are performed here detail, so I'll not go into detail here. So you can see that in this J mu nu matrix tensors will be transformed in this particular form, and this P mu, which is the momentum, for momentum, which transform like in this through this Lorentz transform matrix only. Okay. And now we can perform this expansion of this u, and you will get such interesting relation which will give you the commutator relation between the j mu nu and the p mu nu and the vice versa. These are basically the fundamental interesting parts. So j mu nu rho sigma commutator is basically written down in terms of this metric. Okay, p rho and j mu nu equal to this one. So you can see that they do not commute, but p mu p rho they commute. So the translation generators commute among themselves, but rotation and the translation they do not commute. That means if you perform the translation and then the rotation, or vice versa, they do not signify the same thing. And here you can define a new vector like omega or w mu, which is half epsilon mu nu rho sigma p nu j rho sigma, and such that the w mu p nu equal to not particular 0. And w mu commutes to the p nu, but if you take the commutator w mu and j alpha beta, okay, which contains the rotations, so they do not commute. And also you can calculate the omega mu omega alpha commutator, which written in terms of this, which is like more like a closed algebra, right? So now you can define something called omega on w square, which is w mu, and that's written in terms of the p square and the j's in this way. So we'll see what is the implication of that thing later. So now you can think of like a finite Lorentz transformation that actually always helpful to understand the generators and the in more detail. So here the lambda omega equal to exponential minus I by 2 omega mu nu s mu nu. So omega mu nu is the parameter here, right? And s mu nu are the generators here. So ji, which is the rotation generators, are given as half epsilon ijk sjk. Okay, and ki is the boost generators, which is written as si0, and s00 or the sii, all the elements are basically 0. Now you can see that JI-JJ commutator is related to your JL commutator, KI-KJ commutator related to JL, and KI-JI related to JJ equal to related to some KL. That means basically J and K, their actions are not independent to each other. Okay, so we cannot just segregate it to set of actions based on these J's and K's. So this group actually in either SO13 or SO31, depending on how to define the signature. You can complexify that and you can written down like SO4, C. And then what you can do actually, you can perform a complex linear combination of weak rotation in the generator basis. So you can write down this new set of generators where the I runs from 1 to 3. Mi equal to half Ji plus I kappa I, and Ni equal to half Ji minus I kappa I. If you define in this way, then you will find out that Mi Nj commutator is basically related to ML, and Ni Nj commutator related to NL, while the Mi Nj commutator for all choice of Ij is basically 0. That means basically M, the algebra derived or dictated by this M, is close among themselves, and the algebra dictated by this N, that's also close among themselves. So we can we can segregate it into two orthogonal patches, SO4, C as SL2C plus SL2C, or you can write down in the good form like SU2 cross SU2. So this M generators will form one SU2, and this N generators will form another SU2. So now in the same line of thoughts, if we add this translation and then it is extended, so you have this rotation, this Lorentz transformation as well as the translation. So then for the translation, you have these generators P nu, so which commutes among themselves, but they do not commute with the J rho sigma. Okay, so that's why this we can call this a semi-direct product. Okay, and translation is itself an invariant subgroup of the Poincare group. And here we can define the Casimir apparatus, which is like p nu, which is the mass square, okay, which is the invariant under those Lorentz transformation as well as the Poincare transformation. Okay, and then we have this w mu, which is the w square. Okay, and that gives you the Pauli-Lubansky, which is gives you the basically spin. So spin is also spin square, S square matrix or w square is also a concept quantity. These two Casimir operators one can find out. Now we can classify based on different choices and of this Poincare transformation. So we can see this time-like scenario. Then if you consider this p square equal to m square greater than 0 and p0 greater than 0, then you can define your p mu to be m00, and the little group is basically your SO3. For time like where p square greater than 0 but p not less than 0, energy is less than 0, then you define the minus m000, and then it has the same little group SO3. Because light like that implies p square equal to 0 and p0 greater than 0, so omega 00 omega, then it is like a E2 is the little group, and the same thing with the p0 less than 0, its little group is also A2, because the space like where p square equal to minus n square less than 0, the 0 and because p square equal to minus n square, then that is like a non-compact little group. So you get the SO2 comma 1 for the null vector p mu equal to 0, or everything is 0, the actually the little group is SO3 comma 1. The Poincare group is a 10-dimensional non-compact group with Lorentz group as its subgroup. Okay, and so we'll talk about. So this is the basically what I'm trying to give you, the basically the basic glimpse of the Lie groups and the Lorentz group and those things that we probably already know about this thing. But we'll revisit all these groups in much more detail when we talk about the characters and all those things. Okay.